Good morning, students. Today we'll start the next topic of chapter number 3, which is classification of elements and periodicity in properties. In the last lecture video, you have studied about the need for classification of elements and the historical developments of the periodic table, then the Dobberinius triad and the failures of the Dobberinius triad. Then came Newland's law of octave and the reason behind the failure of the Newland's law of octave, and then came the Mendeleev's periodic law. But due to some reasons, it also got failed because it had many demerits. But Mendeleev made a remarkable contribution to the classification of the elements, and on the basis of the physical and chemical property of the elements, he gave a law known as the periodic law. It states that the physical and chemical properties of the elements are the periodic functions of their atomic weight. Okay, so because of this law, there came many queries among the scientists, and then they tried to find out the reason of the failure or the demerits of the Mendeleev's periodic table. So our topics for today is the modern periodic law and the present form of the periodic table. Okay, so this is a topic which we will study today and many more topics. So, in 1913, a young scientist called as Henry Moseley discovered a relationship between the X-ray spectra and the atomic number of the element. So, when high energy electrons were focused on a target made on an element which was under study, the X-rays were generated by those elements, and observed that energy electrons were focused on a target made of the elements which were under study, X-rays were generated. He studied the frequency of X-rays which were emitted from those elements and observed that the frequency of those prominent X-rays emitted by an element, they were proportional to the atomic number, but they were not proportional to the atomic weight. Moseley did an experiment and where he found a relationship between the frequency root and the atomic number. So he described its relationship like this: root V is proportional to Z, where Z is the atomic number, or we can also write it the number of protons. Okay, so where V equals to the frequency. Okay, so this was that the frequency of X-ray root was proportional of Z, proportional of atomic number. Okay, so this made a conclusion where V equals to the frequency. Okay, so this was the experiment done. So this frequency is a characteristic property of an element and which was equal to the atomic number of which was equal to the number of protons. So this experiment of Henry Moseley concluded that the atomic number is a more fundamental property and not atomic weight. So atomic number, not atomic weight, is the fundamental property of an element or an atom. So therefore he suggested that the atomic number instead of atomic weight should be the basis of classification of any element, and the acceptance of the atomic number as important characteristic of an atom led to the modern periodic law. So the modern periodic law is modern periodic law. It is the physical and chemical properties of the element are periodic functions of their atomic number. So when the elements are arranged in the order of their increasing atomic numbers, it is observed that the elements of similar properties they repeat after the regular intervals, or they repeat periodically. So as a result of this, the elements fall in a certain groups and lead to the arrangement which is called as the periodic table. Now the general plan of the table is it is based upon the atomic numbers, but again it is based upon the electronic configurations of the atom. That's why the electronic configuration bases on the atomic number, so it is based upon the atomic number. Okay, now after this there came the nomenclature of the elements. So the nomenclature of element with atomic number more than 100. Okay, so how did the scientists find out the names or the nomenclature of the atomic number having the atomic number more than 100? So we have elements these days. By today we have elements up to 114. Well, we have elements up to 114, but all of them are not named. Still the recent discoveries are the experiments are being done on the elements. So actually in the recent years there has been many disputes regarding the original discoverers of the elements, because the new elements in the long time back the elements were named upon the names of their discoverers. So because the new elements are very very high in atomic number and they are quite unstable, and only very minute quantities or sometimes only few atoms of these elements are highly required to find out the difference, and it's very costly and sophisticated and also requires laboratory. So such type of work is carried out with very very competitive spirits and all. So the scientists all around the world, which they have a union which is called as a nomenclature of inorganic chemistry, and the IUPAC, which is International Union of Pure and Applied Chemistry, they found out a method of naming these elements. The names of some elements with atomic number 110 and above has been yet to be officially announced, but to solve all these problems the IUPAC recommended nomenclature which is to be followed of the naming of these new elements until their names are officially recognized. So this nomenclature is based upon the Latin words which is like I'll tell you. So like we write digits. Okay, so digits are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So the Latin words for these number are little different. So Latin words. So IUPAC use these Latin words because Latin words are, they are not number in use, so there is no need for the change. So for 0 they write nil, and for 1 they write un, for 2 they write bi, for 3 they write tri, and for 4 it's quad, for 5 it's pent, then hex for 6, sept for 7, oct for 8, and n for 9. Okay, and they also have some initials. So the names are derived by combining together the root, these Latin words, in order of the digits. Example, I'll write the name of 104 atomic number element. So an element having atomic number 104. So the name will be written as, so it's 1 here, so it will be un, and then it will be 0 here. So for 0 it will be nil, and again 1, so it will be un. And then they will also add ium. That means un for 1 plus nil for 0 plus, and then again un for 1, and they will add ium. So the name will be un nil unium. This is how they name. So the IUPAC name of those elements which are official name is yet to be decided. They just have name in this manner. So some of these have got official names, like here in the book you can see that these are the names of the elements which are based upon this technique of naming. Some of them have already been named, like mendelevium and then nobelivium, on the scientist who finds about all these things, but still some of them are yet to be named. Okay, so now coming to the long form of the periodic table. The long form of the periodic table means the modern periodic table. So let's study about the modern periodic table. Modern periodic table. Okay, so this modern periodic table is it is constructed on the basis of the repeating electronic configuration of the atoms, and when the elements are arranged in the order of the increasing atomic numbers, then the long form of the table have some structural features. So that means it has two different things. That means it has an horizontal rows, okay, and then it also has vertical rows. So the horizontal rows in a modern periodic table is called as periods, and the vertical row in the modern periodic table is called as groups. So we have 7 periods and 18 groups in the modern periodic table. Okay, so in terms of the electronic structure of an atom, a period consists of a series of the elements whose atoms have the same number of electronic shells, which is called as the principal quantum number. Principal quantum number, which we denote by the letter small n. Okay, so this means that the filling of the next higher principal energy level will be 1, n equals to 1, then n equals to 2, and then n equals to 3, etc. So there are 7 periods, and each period start with a different principal quantum number. So like we have 7 periods, so we'll study a little bit about all these 7 periods. How do they the filling of the electrons is done in these periods. So before this, let's have a study, have a look on this modern periodic table. So okay, let's take. So here, as you can see, you have also learned in your class 10th, but see, in this periodic table modern, we have 4 blocks, which is S block, then P block, which we studied in class 10, then in the center it's D block, and then it's F block. So it's S, P, D and F block. Okay, so it starts with the atomic number 1. Okay, so 1 here and then 2 is here in the last. Can you see properly? Okay, so actually what happens, this S block has 2 groups. Okay, so this is the vertical row and this is the horizontal row, and horizontal row has 7 periods, which is 1, 2, 3, 4, 5, 6 and 7. So horizontal row has 7 periods and vertical rows have 18 groups. So from 1 to 18 groups. Okay, now in the this first group, all these are the alkali metals, and second group is called as alkaline earth metal. So this hydrogen is not a part of the alkali metal group, but it is placed above here. So this S block elements, all the S block elements have almost same property, but this hydrogen is not part of an S block element. It has a special case. Okay, so then coming to this P block element. So P block starts from the group 13. So from group 13 to group 18 we have P block elements. So all these elements are from group 13. So these are the P block elements, which are generally non-metals, and these are generally metals. So in the center, in the middle, from group number 3 to group number 12, it is D block elements, which are also called as transition elements. So the reason they are called as transition elements, because their property keeps changing. That means they show transitions. That means there is a transitions from this group to this group. So because this was the metallic group and this is the non-metallic group, so these metals, so the property of the elements will change from the metal and it will transition to the non-metal. So this group is of heavy elements and they show high transitions. So and then this F block, it is not placed in this table, it is outside the table. It is also called as F block elements, which is light transition elements, which also shows some transitions. And these series are the part of this. They are the part of this 6th period. So this is a star which you can see here. So after the lanthanide, so they all these elements has to be fitted in this section. So because there is no space, and if we'll put these, so the table will be disturbed. So in order not to disturb the table, they have kept them in another block. So this lanthanides, they are supposed to be here, so they resemble the property of this period. And then the actinoids are here. Actinoids, you can see the star here. So all these elements are fitted in this group. So that means that in the first group, in the first group, or in the first period, actually in the first period, we have a configuration. We have some numbers which are sometimes called as magic numbers. So if you see that in the first period there are only two, we have 2 shells. Okay, so the filling of the electrons, maximum filling of the electrons will be 2, and the maximum filling of the electrons in second period will be 8, and then again 8, and 18, 18, 32 and 32. So if you'll count here, the number of elements in this is 1 and 2 in the first period. Then in the second period it's 8, 1, 2, 3, 4, 5, 6, 7 and 8. Again it will be 8 in the third period and 18 in the fourth period, if you'll count. And in the fifth period it will be again 18, and in the sixth and seventh it will be 32. So 18 here and 18 here, 32 and 32. So it's 8, it's 2, 8, 8, 18, 18 and 32 and 32. This is how the modern periodic table looks like. Okay, now after this we will again move to the long form of the periodic table. So in this we have horizontal row, which resembles the period. So the elements of the first period. So the first period, So the first period, which corresponds to n equals to 1. So this is unique because it contains only 2 elements. Okay, so it contains only 2 elements, so it has only one first shell, which is K shell, and it has the first element is the hydrogen, and the second one is helium. So the first period contains only like hydrogen, only one s, and helium contain only one s2. So this is the first period. This is the configuration of the first period, 1s1 and 1s2. So for the second period, it contains 8 elements. As I've told you, it contains 8 elements, or because here n equals to 2, and it also has like, I'll tell you how it will work. So it will have 1 2s, 1 or 1 2s, and 3 2p in the second shell, which is L shell. So total it will be having 8 elements in the second period. So like in this configuration, there are other rules also which you have not studied in your class 10, but you will be doing it in chapter number 2, since the chapter number 3 was started first. So that's why maybe all the doubts will be clear to you when you will study about chapter number 2. So I just want to tell you that if you want to write the configuration, or if you want to study the configuration, you can do in a simple way, that you just have to write like it's 1s, 2s, 3s, 4s, 5s. Okay, then you'll write s, 2s, and 2p, 3s, 3p, and then 3d, because it's spdf. Okay, then 4s, so we will just leave 1 1 1. So 4p, 4d, and 4f. Okay, so 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and then 5s. We'll just leave it. So now when we'll move from up, so it will be like this. So it will be coming 1s, and then it will be 1s, 2s, and then it will be 2p, 3s, and 3p, 4s, and then 3d, 4p, 5s. Okay, so let's start. It will be in the first in the first shell, it will be 2 electron maximum, 2 electrons, as we have studied about 2. Then in the second it will be 6, not because it has to be overall 8, है ना? So if it has to be 8, so it's 6 plus 2 8. Again it has to be 6 plus 2 8. Then in the third it has to be 18, so it could be 10, and then it has to be like, it could be 6, and again it has to be 2. So if you will count it, it will be 10 plus 6 plus 2, so 18 here, and then it can be same like this 10, and then it will be 14. So if we keep on placing these s and s here also, so it will be 18 to 8 to 8 18, and 2 8 8 18 18 32 and 32. So when we will write it, the configuration, it will be 1s2, then we'll move again to 2s2, then 2p6, then 3s2, then again 3p6, then 4s2, then 3d10, then 4p6, then 5s2, and so on. It will move on, so on. So this is how we write the configurations of the element. Okay, so this is not that it has to be like this. It's the minimum filling of the shell. This is how we have to learn now the configurations. Okay, so now in the elements in the third period, the elements of third period, it has to be the n equals to 3. So the orbitals, there are 9 orbitals, and one will be 1 3s, then 3 then 3p's, then 5 will be 3d. So it means that it will be 3s 1 3s, 1 3s, and then 3p, and then 5d. Okay, 3 5 3d. So I hope it's clear now. So this is how by this the configuration is done, and the elements are filled in the first period, second period, third period, and fourth period. Okay, so in this manner the filling of the elements in every period is done. So with this I end this video. So in the next video we will be studying about the general formulas of the elements and division of the element into the S, P, D and F block. So these things which I have taught you today will be more clear when we'll study about the general characteristics of each block. Okay, thank you.